All right, let's take a look at some reactions involving organic compounds. This first one here, of course, is a review. Many organic compounds can undergo combustion reactions, and what is produced when a hydrocarbon burns depends essentially on the amount of oxygen available. So we focus primarily in this class on what we call complete combustion, where we have lots of oxygen, enough oxygen to completely oxidize the carbon in the hydrocarbon, and it's oxidized completely to carbon dioxide. So if we have, I'll just write the hydrocarbon as CXHY. Could be methane, could be ethane, propane, could be an alcohol, all kinds of different things. So if it reacts with lots of oxygen, then we make carbon dioxide along with water. So again, the carbon is completely oxidized to carbon dioxide. Incomplete combustion involves a situation where you have a limited amount of oxygen, not enough oxygen to completely oxidize the carbon to carbon dioxide. A couple different situations. We have just a limited amount of oxygen, enough definitely to support combustion, but again, once again, not enough to turn that carbon into carbon dioxide, but rather into carbon monoxide. And then if you have just enough oxygen to support combustion, we call this very limited amount of oxygen, you'll get a yellow flame, and the flame will also be very sooty. So if you ever see, black smoke being produced from combustion of some hydrocarbon, it's because of a lack of oxygen. And so in this case, again, we have the hydrocarbon reacting with oxygen. It is oxidized not to carbon dioxide nor carbon monoxide, but just to carbon. And that's where the soot comes from. So you'll be told as one way or another whether there's plenty of oxygen, a limited amount of oxygen, or very limited amount of oxygen. So just make sure you know the products of those reactions. So I keep mentioning that the carbon is oxidized, so that implies that combustion reactions are redox reactions, which they are. And so during the combustion of a hydrocarbon, carbon in the hydrocarbon loses electrons and thus is oxidized. So if you think about, say, carbon in methane, so let's look at the equation for the combustion of methane. What is the oxidation state of carbon in methane? Let's go ahead and pause and think about that. So in methane, carbon has an oxidation state of -4. So remember, each hydrogen is +1. What is the oxidation state of carbon in carbon dioxide? Go ahead and pause and think about that. Each oxygen is -2, so that means carbon is +4. So we're going from -4 to +4. Oxidation state increases by quite a bit. And in these reactions, hydrocarbon combustion, the oxygen gains electrons and is reduced. So oxygen in O2 has an oxidation state of, that would be 0. And in most compounds, such as carbon dioxide and water, oxygen has an oxidation state of -2. Its oxidation state is going down, which means that oxygen is being reduced. So let's do this. Let's balance this equation first. The combustion of methane in unlimited amount of oxygen. And so we need 2 waters and 2 oxygens. So as long as we have a ratio, mole ratio of at least 2:1 oxygen to methane, we will produce carbon dioxide. So let's take a look at a couple examples. Let's write the balance equation for the combustion of methane in the presence of a limited amount of oxygen. Limited. So go ahead and pause the video and write that balance equation. So we see here, if you have less than a 2:1 ratio, so I balance this with keeping the methane as a 1. We'll do that in the next example as well. We see that if there's less than a 2:1 ratio of oxygen to methane, then you don't make carbon dioxide, but rather carbon monoxide. So still, a lot of oxygen, enough oxygen for the combustion reaction to occur quite well, just not enough oxygen to make carbon dioxide. In reality, you're going to get a mixture of products anyway, so you're going to have situations where oftentimes both carbon dioxide and carbon monoxide are produced, but we're going to just stick with one or the other when we write our equations. All right, next one. I think you know what's coming. Go ahead and write the balance equation for the combustion of methane in the presence of a very limited amount of oxygen. Go ahead and pause and do that now. So if you have less than 2 to 1, less than 1.5 to 1, so if we have a 1-to-1 ratio of oxygen to methane, you are not going to make carbon monoxide, you're not going to make carbon dioxide, you are going to make carbon, of course, each time along with water. All right, and here's where it starts to get interesting with our reactions. We'll start off with substitution reactions of alkanes. Should be noted, and we mentioned this before, that alkanes are quite unreactive. So we have saturated hydrocarbon, the carbon-carbon bonds, the carbon-hydrogen bonds are relatively stable, and so an alkane by itself is relatively stable and doesn't want to undergo change. There's a particular reaction, though, involving alkanes known as free radical substitution, and this occurs via the homolytic fission of a halogen is usually the case. So let's take a look at an example reaction of chlorine gas, and again, could be any other halogen, fluorine, bromine, or iodine, and methane. Again, could be any other alkane, but we'll start off simple. Thus to limit the products, because if we have a more complex hydrocarbon that is undergoing this reaction, say ethane or propane or butane, and then we're going to get many, many, many possible products. So we'll just keep it simple for now. All right, so first step, name implies, is called initiation. So it should be noted that this reaction does not occur just all by itself. If you were to take methane gas and chlorine gas and mix them together, guess what would happen? That's right, absolutely nothing. So this reaction only occurs in the presence of UV light, and that is really, really, really important. Without the UV light, this reaction does not occur. So in this first step, the initiation, 2 chlorine-free radicals. We talked about what a free radical is last time. 2 chlorine-free radicals form when exposed to ultraviolet light. So let's take a look at that. So we have our chlorine molecule, and we have a homolytic fission. So we talked about that where when the bond breaks, the pair of electrons, one of the pair goes to one atom and the other pair goes to the other atom. And so we show that with our one-headed arrow. So something like that. We have to show in the equation that this process does not occur by itself, but rather occurs in the presence of UV light. So we've seen this before with catalysts. We'll see this again later on with catalysts. We can include ultraviolet light here as well. So any reaction conditions that are needed for the reaction to occur, we can put above the arrow. If it's heat, or if it's a particular catalyst, or in this case, ultraviolet light, we can indicate that by putting it over the arrow. So what we end up with are 2 chlorine free radicals. They have unpaired electrons. As I mentioned last time, these are very, very, very reactive. Many atoms or molecules do not like to have an unpaired electron. All right, our next step is called propagation. And so we have a couple different options here. One, a chlorine free radical may react with a methane molecule. So let's take a look at that. And what do you make when this occurs? So in this case, what happens, you make a methyl radical and hydrogen chloride. So the hydrogen from methane, one of them goes to chlorine to make hydrogen chloride. and then you're left with a methyl radical. Another possibility is that, and again, this has to occur after the formation of a methyl free radical. A methyl free radical may react with a chlorine molecule. So let's take a look at that. What do you think the products are of this step? Well, we get substituted methane, so we have a chloromethane molecule. And once again, we end up with, this case, a chlorine-free radical. So we see each step in propagation, we form a new substance, but we also form another different free radical. All right, then lastly, we have termination. So make sure, again, you're familiar with these steps. We have initiation, formation of free radicals, propagation, formation of new substances along with the formation of more free radicals, and then termination. This occurs when two free radicals combine, any two, whichever you have. So if you have two chlorine free radicals, they are going to combine to form molecular chlorine. Or if you have a chlorine free radical and methyl, whoops, let's fix that, chloromethane. And then what if you had two methyl free radicals? What do you think those combine to make? So we have several different products that are possible. Usually the overall equation that occurs is this. This is how we write it. So we have methane or any other alkane reacting with chlorine in the presence of UV light to make chloromethane in hydrogen chloride. So this is the monosubstituted alkane. Is it possible to get a di or tri or tetra substituted alkane, meaning CH2Cl2 or CHCl3 or CCl4? Absolutely. So this is just one of the possible products for this reaction. And so we'll focus on this now, the monosubstituted product. And so this is overall what happens during the reaction. Again, the key is that this reaction will only occur in UV light. In the next lesson, we'll be learning about addition reactions. Technically, these are called nucleophilic addition reactions. A nucleophile, whoops, sorry, I got ahead of myself there. This is not a nucleophilic, this is an electrophilic. Electrophilic addition reaction. An electrophile, phile means loves. An electrophile is a substance that loves electrons or loves negative charge. And so we're going to look at these reactions. I just want to introduce it now, and so we can spend some more time on it later. Let's just go to the overall equation, and then I will explain in our next lesson how this occurs. So let's say we have ethene. So mentioned before that alkenes are very reactive. The electrons that make up the pi bond being delocalized allow this substance to undergo addition reactions. Now, what's important is understanding the names of these reactions. So substitution reaction that we just saw, you're substituting a chlorine, let's say, for a hydrogen. They switch. Addition reactions is we're adding something. We're going to add something to the carbons across the double bond. So let's look at the overall equation for the reaction, let's say, between ethene and any halogen. We'll just do chlorine, I suppose. Now I can write it a couple different ways. With the overall equation, normally, and I'll explain when this is not the case, but normally we're using chemical formulas in the overall equation for a reaction. So ethene has a chemical formula C2H4. And let's say it reacts with chlorine. This reaction does not require any specific conditions or any specific reagents. Like I said, alkenes by themselves are very reactive. And so this reaction will occur all by itself. And what do you make? You make the disubstituted halogenoalkane, this is called. Whoops, that is C2H4. Sorry about that. Disubstituted. So we have both chlorines are added to carbons, and moreover, they're added to carbons across the double bond. So I will show you the mechanism for this next time. I just wanted to introduce our next reaction type, and I wanted to point out the difference between a substitution reaction and this reaction, an addition reaction. All right, that concludes this lesson. Thanks for watching.